C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 6. Now, let's explore Chapter 6, Introduction to LlamaSharp. Turning our attention to theoretical foundations. The theoretical foundation of running large language models, LLMs, locally within the .NET ecosystem represents a paradigm shift from the traditional cloud-centric API approach to a decentralized, privacy-preserving, and latency-optimized architecture. To understand LlamaSharp and its role in edge AI, we must first dissect the underlying mechanics of how these models function, the mathematical transformations they perform, and how C# acts as the orchestration layer bridging high-level logic with low-level native execution. Now, let's talk about the nature of local inference, from tensors to tokens. At its core, an LLM is a massive mathematical function, a transformer, that maps a sequence of input tokens to a probability distribution over subsequent tokens. When we discuss local inference, we are discussing the execution of this function entirely within the memory and processing constraints of the user's device, bypassing network round trips and external servers. The analogy of the bilingual librarian: imagine a librarian who speaks only English. To translate a book from French, they do not translate word for word in real time. Instead, they have memorized the entire statistical structure of both languages. When you hand them a French sentence, they instantly recognize the patterns and generate the most statistically probable English equivalent. Cloud AI is like calling a specialized translation agency. You send the text, wait for them to process it, and they mail it back. It is accurate but slow and requires trust. Local AI, edge AI, is like having that librarian living in your house. The knowledge, the model waits, is on your shelf, your disk. You ask a question, and the answer is immediate and private. LlamaSharp is the interface you use to speak to that librarian. It handles the complex formatting of your request, the prompt template, and interprets the librarian's mumbled responses, the token stream, into coherent text. Turning our attention to the computational graph, the transformer architecture. To understand why C# needs a specialized wrapper like LlamaSharp, we must look at the computational heavy lifting involved. The transformer architecture, which powers models like Llama and Phi, relies heavily on matrix multiplication and attention mechanisms. 1. Embeddings. When you input text, it is first tokenized, broken into chunks like the cat, sat. Each token is mapped to a high-dimensional vector, an embedding. In a 7B model, this might be a vector of 4096 floating point numbers. 2. The attention layer. This is the reasoning engine. It calculates how much every word in the input should attend to every other word. This requires massive matrix multiplications. Analogy: think of a crowded room where everyone needs to whisper to everyone else to decide on a group decision. The attention score determines how loudly each person listens to others. In a 70B model, this room has 70 billion participants. 3. Feed-forward networks. After attention, the data passes through dense layers to process the information further. Why this matters for C#: in a standard C# application, you process data using loops and LNQ. However, LLMs require SIMD, single instruction, multiple data, operations. A standard CPU loop is inefficient for multiplying two matrices of size 4096 by 4096. This is why LlamaSharp does not execute these calculations in pure C# managed code. Instead, it acts as a wrapper around llama.cpp, a highly optimized C++ library that utilizes AVX2, AVX512, and CUDA instructions to perform these matrix multiplications at blistering speeds. Now, let's talk about the bridge, native interoperability and p/invoke. LlamaSharp is fundamentally an interop layer. It leverages C#'s ability to call native code via platform invoke, p/invoke. The concept, the heavy lifting, the inference engine, is written in C++ for maximum performance. The logic, UI, and application flow are written in C# for developer productivity and ecosystem integration. LlamaSharp provides the managed C# wrapper that translates C# object calls into C++ function calls. The analogy of the interpreter: imagine you are a conductor, C#, leading an orchestra of musicians who only read sheet music in a foreign format, C++ binary. You cannot force the musicians to learn your language instantly. Instead, you have a translator, LlamaSharp, standing next to you. When you gesture, start Symphony No. 5, the translator signals the lead violinist, the C++ backend, to begin. The violinist plays, executes the inference, and the sound, the output tokens, flows back to the audience, your application. In C#, this is implemented using unsafe contexts and pointers to memory handles. When LlamaSharp loads a model, it allocates a block of unmanaged memory, outside the .NET garbage collector's reach, to hold the billions of parameters, the weights. The C# Llama model object is merely a lightweight handle to this massive unmanaged blob. Here, we're establishing a crucial bridge between our C# application and a native C/C++ library, specifically llama.cpp. Notice the using system, runtime.interop services, directive at line 2. This namespace is absolutely essential because it provides the DLL import attribute, which is the cornerstone for platform invoke, p/invoke. P/invoke is a technology that allows managed code, our C#, to call unmanaged functions in a native DLL. Without this, our C# application would be completely isolated from the high-performance C/C++ code that powers llama.cpp, which is optimized for tasks like loading large language models and performing inference efficiently on various hardware. The public static class native bridge at line 4 serves as a container for these native function declarations, making them easily accessible throughout our C# codebase. At line 7, DLL import, llama, calling convention equals calling convention, decl, is the magic. It tells the .NET runtime to look for a DLL named llama, which would be llama.dll on Windows, liblama.so on Linux, or liblama.dylib on macOS, and to find a function within it. The calling convention, decl, is critical here. It specifies how arguments are pushed onto the stack and who is responsible for cleaning up the stack. Decl is the standard calling convention for C/C++ functions and ensures interoperability. If we use the wrong calling convention, e.g., stdcall, our application would likely crash with a stack imbalance error. Continuing our exploration of the native bridge, at line 8, we declare public static extern int ptr llama_load_model_from_file, string path, modelparams at params. This C# signature directly mirrors a function in the native llama.cpp library. Extern is the keyword indicating that the method's implementation is external and provided by a DLL. The return type int ptr is very important. It's a platform-specific integer type used to represent a pointer or a handle. In this context, llama_load_model_from_file will return a pointer to the loaded model's internal data structure in native memory. Our C# code doesn't need to understand the internal layout of this structure, only to hold on to its memory address. The model params at params argument is a C# struct that must precisely match the memory layout of its C/C++ counterpart. Any mismatch in size or ordering of fields would lead to memory corruption or incorrect behavior when the native function tries to interpret these parameters. Similarly, at line 12, public static extern int llama_eval, int ptr_ctx, int tokens, int n_tokens, int n_past, int n_threads, declares the native inference function. Llama_eval takes the int ptr_ctx, the context pointer obtained from llama_load_model_from_file, an array of tokens, representing the input prompt, and several integer parameters controlling the inference process. The return type int would typically indicate a status code or the number of tokens processed. These declarations are the direct contract between our managed C# world and the unmanaged C/C++ world, enabling our C# application to orchestrate complex operations like loading and running large language models without rewriting the core high-performance logic. Now, let's talk about quantization, the art of lossy compression. One of the most critical theoretical concepts in local LLMs is quantization. Standard models are trained using 16-bit floating point numbers, FP16, or 32-bit, FP32. A 7B model in FP16 requires roughly 14 GB of VRAM. This is prohibitive for most consumer hardware. Quantization is the process of mapping these high-precision values to lower-precision integers, e.g., int4, int8. The analogy of the photographer's portfolio, FP16, full precision. A photographer prints a portfolio on museum-grade paper with archival ink. The colors are perfect, the gradients are smooth, and the file size is massive. It requires a large, climate-controlled vault to store high VRAM. int4, quantized. The same photographer creates a thumbnail JPEG of the images. The essence of the image remains, you can still recognize the subject, but the fine details are smoothed over. The file size is tiny, and you can carry thousands of them in your pocket, low VRAM. The GGUF format, LlamaSharp primarily utilizes the GGUF, GPT-generated unified format, file format. GGUF is designed specifically for this quantized workflow. Unlike the original PyTorch checkpoints, .pth, or the Hugging Face safe tensors, GGUF bundles the model architecture information and the quantized weights into a single file, optimized for fast loading by C++ backends. Why this matters for Edge AI? In a C# application targeting edge devices, like an industrial IoT gateway or a laptop, memory is finite. By using LlamaSharp to load a 4-bit quantized GGUF model, a 70B parameter model, which would normally need 140 GB of RAM, can run on a machine with just 16 GB of RAM, albeit slower. This trade-off between precision and resource consumption is the central optimization challenge in Edge AI. Turning our attention to context management and the KV cache. LLMs are stateless by default. They do not remember previous interactions in a conversation unless explicitly fed the history back into the input. However, reprocessing the entire conversation history for every new token is computationally wasteful. This is solved by the key value, KV, cache. The analogy of the meeting room: imagine a meeting where every time a person speaks, they must introduce themselves and repeat everything they said previously. This is inefficient. Instead, the meeting has a whiteboard, the KV cache. When a person speaks, their point is written on the board. When the next person speaks, they read the board to understand the context, then add their point. The input, the new user query. The cache, the history of the conversation, stored as mathematical representations of previous tokens. The output, the next predicted token, based on the new input plus the cached history. In LlamaSharp, the LLama context object manages this cache. It allocates a contiguous block of memory to store the past key and value tensors for every layer of the model. As the conversation grows, this cache expands. If the context window is exceeded, e.g., 4096 tokens, the oldest tokens are dropped, sliding window attention, and the cache is shifted. Moving on to prompt templating and tokenization. Before inference can begin, raw text must be transformed into the specific format the model expects. Llama and Phi models are not just raw text processors, they are trained on specific chat templates, e.g., user_n, prompt, assistant_n. The tokenizer, C# strings are UTF-16 encoded. LLMs operate on tokens, integers. The tokenizer is the dictionary that maps hello to 15496. Subword tokenization: modern tokenizers, like byte pair encoding, break words into chunks. Unfriendliness might become unfriendliness. Vocabulary mismatch: a standard C# string, split, is insufficient. You must use the exact tokenizer vocabulary shipped with the model. LlamaSharp handles this by loading the tokenizer.model file alongside the GGUF weights. The analogy of the diplomat: you, the C# application, speak plain English. The model, the LLM, speaks a specialized technical dialect. The diplomat, tokenizer/prompt template: before you send your message to the model, the diplomat rewrites your message into the exact format the model understands. If you omit the template, the model thinks you are continuing a narrative rather than asking a question, leading to hallucinations or non-sequiturs. Let's discuss inference parameters, the steering wheel. Once the model is loaded and the prompt is formatted, the generation process begins. This is controlled by sampling parameters, which dictate how the model selects the next token from the probability distribution. 1. Temperature. Concept: a scaling factor applied to the logits, raw output scores, before softmax. Effect: high temperature, greater than 1.0, flattens the probability curve, making the model more creative and prone to errors. Low temperature, less than 0.5, sharpens the curve, forcing the model to pick only the most likely tokens, resulting in deterministic, repetitive output. Analogy: imagine a chef choosing ingredients. Low temperature is a strict recipe: always salt, always pepper. High temperature is experimental cooking: might use salt, might use sugar. 2. Top K and Top P. Nucleus sampling: Top K limits the selection pool to the K most likely next tokens. If K equals 50, the model ignores the 50,000 other possible words. Top P limits the selection pool to the smallest set of tokens whose cumulative probability exceeds P, e.g., 0.9. This is dynamic: if the model is very confident, the pool might be small; if unsure, the pool expands. Why use them? Without these limits, the model might pick a statistically rare but grammatically correct word that derails the logic. These parameters act as a guardrail for coherence. Moving on to the execution loop. The theoretical flow of a C# application using LlamaSharp follows this cycle. 1. Initialization: load the GGUF file into unmanaged memory via the C++ backend. 2. Prompt processing: input string -tokenizer list of integers. These integers are passed to the context to fill the initial KV cache, the prefill phase. 3. Generation loop: step A, feed the current token, or the last generated token, into the model. Step B, the model outputs a raw logit vector, size equals vocabulary size, e.g., 32,000. Step C, apply temperature, top K, top P, and frequency penalty, to reduce repetition. Step D, apply softmax to convert logits to probabilities. Step E, sample a token based on these probabilities. Step F, decode the token ID back to a string fragment. Step G, yield the text to the C# async enumerable string a stream. Step H, update the KV cache with the new token. Repeat until the end of sequence token is generated or the max length is reached. Moving on to integration with modern C# features. In modern C#, Net 6/7/8, this architecture leverages specific features for efficiency. Async enumerable LLM inference is inherently a streaming process. Instead of waiting for the full response, which might take seconds, C# allows us to yield tokens as they are generated. This enables real-time UI updates in Blazor or MAUI applications. Span T and memory T. When passing token arrays between C# and the native C++ backend, we must minimize memory allocation overhead. Span allows us to slice arrays without copying, which is critical when processing large batches of tokens. Disposable and safe handle. Since the model weights reside in unmanaged GPU/CPU memory, C# must strictly manage their lifecycle to prevent memory leaks. LlamaSharp objects implement disposable, ensuring that when the using block ends, the native memory is explicitly freed back to the system. Now, let's talk about ONNX versus native, GGUF/CPP, workflows. While this chapter focuses on LlamaSharp, which uses the native C++ backend, it is vital to understand the alternative, ONNX runtime. Native, llama.cpp/gguf pros, maximum performance on CPU, specific optimizations for quantization, lower memory footprint. Cons, harder to deploy cross-platform, requires native binaries for Windows, Linux, Mac. Use case, edge devices, local desktop apps, high throughput CPU inference. ONNX, Open Neural Network Exchange Pros, standardized format, hardware agnostic, runs on GPU, CPU, NPU, easy integration with Azure ML. Cons, often requires FP16 or FP32 precision, larger models, less optimized for extreme quantization on CPU. Use case, cloud deployment, Windows ML integration, scenarios where hardware acceleration, like DirectML, is prioritized over raw CPU efficiency. LlamaSharp bridges the gap by abstracting the backend. While it defaults to the native C++ backend for llama/gguf, the architecture is designed to be extensible, allowing developers to swap the inference engine while keeping the C# API consistent. Now, let's explore summary of architectural implications. Building AI applications with LlamaSharp in C# moves the developer from being a consumer of APIs to an architect of systems. You are no longer just sending a string to a black box. You are managing memory lifecycles, tuning mathematical sampling parameters, handling binary file formats, and orchestrating the flow of data between managed and unmanaged memory spaces. This theoretical foundation establishes that local inference is not merely a slower version of cloud inference, it is a distinct computing paradigm requiring careful attention to resource management, model quantization, and prompt engineering, all of which are elegantly handled by the LlamaSharp abstraction within the robust .NET runtime environment. Now, let's explore basic code example. Here is a basic Hello World example for running a local LLM using LlamaSharp in C#. Here, we're bringing in essential namespaces for our application. Notice system.io, which is crucial for file system operations, especially when locating our model file. System, threading, tasks is included because we're performing asynchronous operations, which is a best practice for I/O-bound tasks like loading large models. Most importantly, Llama and Llama, Common are the core libraries from the LLamaSharp project, providing the functionalities to interact with large language models. Without these, we wouldn't be able to load or run our GGUF model. We define our LlamaSharp Hello World namespace, which acts as an organizational container for our code. Inside, the program class is the entry point for our console application. The main method is declared as static async task main, string, args. The async task return type is vital because we'll be performing asynchronous operations, such as loading the LLM, which can take a significant amount of time. Making main async allows us to use await and prevents blocking the main thread, making the application more responsive, especially for longer-running tasks. At line 13, we begin the first logical step, defining the path to our language model. We're assuming the user has already downloaded a GGUF model file, specifically phi2.q4_k_m.guf, and placed it alongside the executable. We construct model path by combining the base directory of the current application domain with the model file name. Using appdomain.currentdomain.base directory is a robust way to locate files relative to the application's executable, ensuring portability across different deployment environments. This avoids hard coding paths, which is a common source of errors in production. This block of code, starting at line 19, performs a critical validation step. Before attempting to load the model, we check if the specified model path actually exists on the file system using file exists. If the file isn't found, we provide clear, color-coded feedback to the user on the console, explaining the error and guiding them on how to resolve it, downloading the model and placing it correctly. This is an essential practice for user-friendliness and debugging, preventing cryptic errors further down the line and ensuring the application fails gracefully rather than crashing. Now, we move on to configuring the execution parameters for our model. We instantiate model params with our model path. The most significant decision here, at line 34, is setting GPU layer count equals 0. This explicitly tells LlamaSharp to offload 0 layers of the model to the GPU, forcing all computation to happen on the CPU. This is a deliberate architectural choice to ensure the example runs out of the box on any machine, regardless of whether it has a compatible GPU or CUDA/RCM drivers installed. In a production environment with dedicated GPU hardware, you would typically set this to a higher number, e.g., 33 for Phi 2, to leverage the significant speed benefits of GPU acceleration for inference. At line 37, we begin the actual loading of the model weights. We use LLamaWeights.loadFromFileAsync parameters to asynchronously load the model. The using var model statement is crucial here. It ensures that the LLamaWeights object, which holds potentially gigabytes of model data in memory, is properly disposed of when it goes out of scope. This is vital for memory management, preventing resource leaks. This loading step is typically the most memory-intensive and time-consuming part of the entire process, as the entire model architecture and its learned parameters are read into RAM. After loading the raw model weights, we need an executor to manage the interaction. Here, we instantiate an interactive executor at line 45, passing in our loaded model. The interactive executor is designed for conversational scenarios. It handles the context window of the LLM, meaning it keeps track of previous turns in a conversation to maintain coherence. It also manages the intricate process of preparing prompts for the model, including tokenization and handling special tokens. This abstraction simplifies the interaction with the underlying LLM, allowing us to focus on the conversation flow rather than low-level model details. Here, we define the prompt that we will send to the language model. The prompt, as seen at line 49, is a simple instruction to generate a haiku. This is our input to the LLM. Following that, lines 51 to 54 are purely for user experience. We print the user's prompt in cyan and then indicate that the AI's response is coming. This visual feedback makes the console output much clearer and more engaging for the user, distinguishing between user input and AI output. It's a small but effective UI enhancement for a console application. This is the core inference loop where the model generates its response. We use await for each var token in executor.inferAsync to stream tokens one by one. This inferAsync method is where the magic happens. The model performs calculations to predict the next most likely token. We pass inference params to control the generation process. Temperature equals 0.7 F, line 62, introduces a degree of randomness. A lower temperature makes the output more deterministic, while a higher one makes it more creative. Max tokens equals 100, line 63, prevents the model from generating an excessively long response. Crucially, anti-prompts, line 64, define strings that, if generated, will immediately stop the inference, preventing the model from generating boilerplate or unwanted conversational turns like repeating user. Finally, at line 68, we print each token as it's generated, giving the user a real-time streaming experience, much like what you see in chat interfaces. This is a great user experience choice, as it provides immediate feedback rather than waiting for the entire response to be generated. Once the inferAsync stream completes, either by reaching max tokens, an anti-prompt, or the model's natural end-of-sequence token, line 70 simply adds a new line for formatting, ensuring the console prompt appears on a new line after the AI's output. This concludes our simple LLM interaction example. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 6 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvas/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.